Hi gang! I get asked every now and then, what is ground? Sometimes it's to do with household ground, this prong and hole in your plug. Sometimes it's about finding a good ground when making something. And sometimes it's ground in an electronic circuit. So I thought I'd talk about each of these. Let's start with household ground. In North America, this roundish hole is ground, and so the prong on a plug that goes in it is the ground prong. But to understand that ground hole and prong, we first have to understand the other two holes. In North America, they're called hot and neutral, and the wires are usually black and white. They're what carry the electricity that powers things. Behind the hole called hot, you'll find a wire that runs behind the walls, and eventually goes to a breaker in your breaker panel. From there, the electricity goes behind the breakers to one of these thick black wires, and then outside your house to a transmission pole and transformer somewhere. The other hole, again called neutral here in North America, also goes to that breaker panel, but not to any breaker. Instead, it goes to this metal bar. From there, the electricity goes along this thick white wire, and then outside your house to the same transmission pole and the same transformer. Here that all is in a diagram. This is the path for the hot, or black wire, to the breaker and out to the transformer. And this is the path for the neutral, or white wire, through the breaker panel and out to the transformer. The other side of the transformer is what continues on to the generating station. So where does the ground hole go? It also has a wire that goes to the breaker panel and connects to this other metal bar, which is connected to the breaker panel's metal case. And it's not clear with this panel, but somewhere the case is connected to the neutral bar. Our diagram now looks like this, with the ground wire going to a ground bar and then onto the neutral bar. But why is the ground wire connected to the neutral bar like that? That's in case you have a break in the insulation covering a wire somewhere. That break can cause a fault, such as in this microwave oven. 3 wires enter the microwave oven. Those 3 wires are connected to the 3 prongs of the plug, hot, neutral, and ground. As we said, the electricity flows through the hot and neutral wires. The 3rd wire is the ground wire. The ground wire is connected to the metal case, and normally no electricity flows through it. We'll add the microwave oven to our diagram. The hot and neutral wires go to the electronics, and the ground wire connects to the case. But the case is not connected to anything else. Electricity won't flow on it because there's no return path. But what if the insulation around the hot wire gets damaged, and the wire itself touches the metal case? The case is now connected to the hot wire. If you were to touch the case, you'd get a dangerous shock. But luckily the ground wire is connected to the case. That ground wire is a very low resistance path for the electricity, and so it will flow from the hot, through the case, through the ground wire, and back to the panel where the ground is connected to the neutral, and back to the transformer, completing the circuit with the hot wire there. However, since that path is such low resistance, the current will be very high. And remember that the hot path goes through a breaker in the breaker panel. The current will be high enough to trip that breaker, disconnecting the power, and making it safe to touch the microwave oven's case again. Let's look at it again, but on the diagram. The problem starts when the insulation on the hot wire breaks, and the wire touches the microwave oven's case. Since the case is connected to the ground wire, we now have this complete circuit along the ground wire to the breaker panel, then along the neutral wire onward to the transformer on the pole, through the transformer's coil, back through the hot, through the breaker, and continuing to the hot in the microwave oven, where it's touching the case. There's very little resistance along that circuit, and so the electrical current will be very high, high enough to trip the breaker, which opens the circuit, making it safe to touch the microwave oven's case again. But wait, none of that had anything to do with the earth ground. Why is the wire called ground? Looking at the breaker panel again, there's thick ground wire connected to the neutral bar here that goes to a metal rod buried in the ground, called a ground rod, or to some other metal that's buried in the earth ground somewhere, like the metal pipe that brings cold water in from the city. And where the neutral wire goes to the transformer, there's another wire that goes down the pole to a ground rod there too. Now our diagram looks like this, with the thick bare wire from the breaker panel to earth ground, and with the ground wire from where the neutral wire connects to the transformer, also down to earth ground. Why have all this wiring all the way to the earth ground, if it didn't play a part in our microwave oven fault? To understand that, we need to learn a bit about electric charge. Electric charge can be either positive or negative. Looking at an atom, the protons locked in the atom's nucleus have a positive charge, and the electrons surrounding the nucleus have a negative charge. Overall, this atom has a neutral charge, though, neither positive nor negative, because it has the same number of positive protons and negative electrons. Like charges repel each other. Here we have an area with extra electrons between the atoms, so the area is negatively charged overall. If we try to bring in yet another negative electron, it feels a repulsion, so it's harder to make it go there. The like charges repel each other. But what if that area was the size of the Earth? Or maybe just your neighborhood? To negatively charge such a large area would take a lot of extra electrons. Similarly, we could positively charge the area by taking electrons from it, leaving more positive protons than negative electrons. But it doesn't matter. The ground is such a large volume that the ground normally doesn't get very charged either way. It remains with a fairly neutral charge. So what's a good ground? A good ground is one that has a large enough volume that it can handle whatever charge you're trying to give it without it ever becoming very charged. Now back to why we're connecting wires all the way to earth ground. One reason has to do with lightning. Remember that the breaker panel case is connected to ground, and so is this microwave oven's case. When lightning strikes nearby, those cases can become charged. By connecting to earth ground, that charge bleeds away to the ground, keeping the cases safe to touch. Let's say the case becomes negatively charged. As we said, like charges repel each other. Since the ground has a fairly neutral charge, the electrons on the case repel along the wire to the earth ground, and they keep repelling until there's an even amount of charge everywhere. Since the ground can take a lot of charge, the overall charge doesn't even out until everything's fairly neutral. And yet another way to look at it is that the negatively charged case has a certain quantity of charge, and the neutrally charged ground has a different quantity of charge. That means they have different electric potentials. A potential difference, or a voltage, exists between them. Since there's voltage between them, if you connect them with a wire, current will flow. Electrons will flow from the negatively charged case to the neutral ground. For a ground rod to work well, the ground does have to be electrically conductive though, meaning it has a low resistance. Dry sand like this is not very conductive, and is a bad ground. But moist soil is fairly conductive, and is a better ground. Also, the more ground you connect to, the better. Here I just pushed some wires into the ground, and it wasn't very good. I even poured water in to help, but it still wasn't great. You can buy copper and galvanized steel rods that are around 6 to 10 feet long, that you can pound into the ground. But keep in mind that cold ground lowers the conductivity, so make sure to drive it below the frost line for winter use. Besides the ground hole in a power socket, where can you find a ground to use? If the current and voltage aren't too high that you get hurt, then your own body can sometimes act as an okay ground. An example where I've done that is with this portable pizza box crystal radio. It's portable because it doesn't need a ground to work, but it works better with one. And if you look closely here, you'll see my hand is on this capacitor plate. The capacitor is one aluminum foil cylinder that slides around another one, and with paper in between. Making a lot of skin contact with the outer cylinder lets it conduct charge to my hand and body. Here, I'm the ground. Often when playing with high voltage, you'll have a ball that's connected to a wire going to ground, and make a spark by bringing that near a charged object, like this Van de Graaff generator. A fairly safe way to ground that, if you don't have a ground rod that you can connect to directly, is to find a metal pipe that you're certain goes into the ground, like this copper cold water intake pipe from the city. Or this metal fence would do, since it makes plenty of contact with the ground. And finally, what about this ground symbol in the schematic for an electrical circuit? Well, it's called ground, but very often it's more of a common reference. For example, this schematic is for this amplifier. Notice that it doesn't contact any ground. In that case, it just means that all these points are connected together. For the circuit board, I soldered all those points to a bare wire in the back. Anything connected to that common reference will have voltages that are relative to that common. A sort of zero for that voltage. There are other ground symbols too. This one means chassis ground, such as the chassis of a car, basically a continuous piece of metal that many things in the car are connected to, including battery negative. Sometimes though, the ground symbol does actually refer to connecting to earth ground. This is the schematic for this power supply, one that you plug into a wall, with the plug that has a ground prong. In this case, the symbol is saying to connect to that ground prong. Though I guess the only hint is that these points are labeled as hot and neutral, the names for the other two prongs in the plug. Well, thanks for watching. See my YouTube channel for more informative videos like this. You can support these videos either through Patreon or through a one-time donation. And if you like these videos, don't forget to subscribe, give a thumbs up, share with your social media, or leave a question or comment below. See you soon!